So we're going to be back to discuss what are the main components on modeling, and these include stocks, flows, and parameters. We have a system where we have inputs and outputs, and inside the system we have internal transformations. And then we have, say, mentioned before that we have some boundaries in the system. Okay, so we are going to now explain the necessary conditions to start making a model. So for making a model, we need to define initial and boundary conditions. We were discussing about the type of models, the models that include dimensions or models with no dimensions. So if we picture the starting point of our model, like in this figure, we want to model from a specific time, which can be time 0, to a final time. If we don't have dimensions, those are the only initial conditions that we may need. Also, well, of course, the parameters values. If we're dealing with let's say one dimension, that will mean that we not only have to define the time, but we also have to define the initial values of this dimension, right? And then also the limit of this. So given starting conditions at time 0 and boundary conditions beyond the domain of interest, solution is progressively carried out for each spatial location at successive time intervals on definite difference grid. So for our models, we are dealing with initial value problems in our models of only time with only time dependency. All right. So one of the variables that we're looking at is time, and then we have to define through time from a set of given conditions known as initial values, right? So we need to define, and these are called initial value problems. So we need to define the starting point of the time, and we also need to define the initial condition of the dependent variable, and which we call it here y. So y is a set of matrices that need to be defined, and this is also the variables that will move through time. But for each of these variables, we need to define the initial value. All right. So we have two categories of initial value problems. We can also discuss about lump models and about distributed parameter models. Lump models are with OD models, and this considers the amount of a stock, but not how the stock is spatially distributed. So it is probably easy for you to understand, but what is important here is to define that even if we're dealing with any system and we're not considering the space, then that will mean that in any region of the system that we're defining, the conditions of the stock, the values of the stock only will depend on time and not on where it is positioned. Okay. So distributed parameter models, which are the rest of the models on 1 and 2 and 3 dimensions, which change over time, are also called models that have an initial boundary value problem. So this is something that now may be clear to you, because now we not only need to define the initial value, but we also need to define the boundaries on each dimension. Okay. So examples of these models, we have say some before, but we also have, well, basically transport of any contaminant in any of the dimensions that we're mentioning, or temperature gradients, okay? So as we say before, distributed parameter models require boundary conditions and initial conditions. But even if we always stress on the boundary conditions in distributed parameter models, we're going to explain what are the boundary conditions in lump models that are also needed. So this is an example of an initial value boundary problem. And I'm going to give two examples of 1D models that can be treated as lump models or as no only time dependency models, okay? So this is the change in concentration of a pollutant that is defined as biochemical oxygen demand along the river, and the change in dissolved oxygen or concentration along the river. So this is a river, and we have changes in concentration of both components due to agricultural runoff or due to industrial wastewater discharge, or discharge of any pollutant that is affecting our system, right? Or something that also can maybe increasing the dissolved oxygen, because here we're not considering that, but dissolved oxygen can also increase due to some processes that can occur in the river, like well, later on we will describe some of these examples. So initial value boundary value problems consider a system as a continuum with gradients in intensive properties. So if we have, if we want to track these two parameters, this VOD and DO, at one space, in one region of the river, and then how these change over the distance, well, they will have variations, right, clearly. And these variations is the spatial variability. And this, we're talking here about concentrations. So we will have the variations in one intensive property. But then these type of systems, as I mentioned before, can be treated as lump systems. How? Well, we can also make segments of this river, and then we can make the assumption that in each section of the river we have a complete mixed system. Okay, so for instance, in the compartment number 1, we will say that DO and VOD in any section of this compartment is the concentration remain the same, and it will only change over time. And then we'll have the section number 2, where the initial conditions of section number 2 will be the final conditions of section number 1, and so on. All right? So spatial variability in intensive property can be represented as a finite set of segments or lumps, each with uniform intensive properties. Remember that in general, when we are doing, when we are modeling systems, our final question, or our question in one of on these problems may be final concentrations or final temperatures, and those are intensive properties. For this, we're going to define stocks as extensive properties, but then we're going to get the values of these intensive properties. This doesn't change, however, the fact that we have established before that the stocks in our models will be extensive variables, okay, in order to have systems that can have inflows and outflows, right? This is another example of an initial value boundary value problem. This is this is a way to see the change in temperatures within a building, right? So the change in color represent change, the difference in temperature, okay? So we are going to consider here a building that is passively cooled by circulating air underground. So in reality, the temperatures vary within each space. So they have different temperatures in the room, roof, room, and ground duct. However, we can analyze this problem by lumping the energy. We're going to talk about enthalpy, and now we're going to explain what is this term. We can lump the energy of each space. So we assume that the temperature within each space is uniform. And in effect, we assume the air in each space is well mixed, right? Because if we're talking about changing energy, it also involves the mass. So we need to define as small spaces where there is we assume that it's a lump system and everything is well mixed, all right? And that's how we change initial value boundary problems to only initial value problems, or 0 to 0D problems. This is an example of an initial value problem, and this is an example with no change on any dimension. So we only have the time, the change in time, the independent variable as time. Still, as I mentioned to you before, we need to define boundaries in these systems. So again, this is to make it clear, this is not an initial value problem, but boundary or extent of system must be decided. So what will be our boundaries on the system? When we're talking about 0D models, our boundaries will be defined by the considerations that we take of the inflows and outflows in our system. So in this case, in the example of the reservoir, we discussed before that we had evaporation, demand, and inflow, and then we will say that seepage was not considered on this model, so this is a boundary in our problem, right? But remember that we say that we also need initial values for our stocks. So now you need to think about what is the value that the reservoir must have. So we need to set initial conditions also for the stock, not only for the time. So we not only need to define the time limits, so we can model this system from time 0 to 1 year, or from 0 to 1 month, or 3 years, etc. But we also need to define the initial value of the stock. So in this case, we may or may not need to have a value that is other than 0 in the reservoir. Think about this. Think about what are the flows that are involved, and if we need to have a value that is other than 0 in our reservoir or not, okay?